Here I have 6 series, and we are asked to determine which converge and which diverge. Very straightforward instructions, and we certainly have the tools to do it, and it's not what I'm going to do in this video. What I'm going to do in this video is summarize all of the tools we've learned about series so far, and then talk about which tool I would use to do each one of these examples. In the next video or videos, we'll go through and do these examples. But for now, I just kind of wanted to look at all of the series stuff that we know that could help us with problems like these. And so here they are, summarized, not written down as rigorously as we saw them in class. And in fact, one of them is missing 2 parts which you could look up in your textbook. But just as a matter of a review, geometric series are always written down in this form where I have a first term and then each next term is formed by multiplying the previous by a constant. So I have an a plus an a times r plus a times r squared, etc., etc. What's nice about a geometric series is I know that they converge when r is in absolute value less than 1, when r is between -1 and 1. And even better than that, they diverge otherwise. That's not the even better than that. The even better than that is I know I can calculate what they actually converge to when the absolute value of r is less than 1. They converge to a over 1 minus r. So that's a really powerful thing, that even if I'm asked just to determine whether a series converges or diverges, the geometric ones are even better, because it's not just a yes or no based on this. It's a, when it's a yes, I actually know the value it converges to. And that's really nice. Next up, what we call telescoping sums. And here's the first example we saw of a telescoping sum in class, where the first term was a 1/2, but we could write it as a 1 minus 1/2 plus the next term 1/2 minus 1/3. What we see is that the 1/2s would cancel and the 1/3s would cancel. And as I continue to go out, the terms right beside each other cancel off, giving me an easy to predict nth term formula, allowing me to take a limit of the sequence of partial sums and find that value. And one thing that sometimes tips me off that I have a telescoping sum is that it might be written down some way like that. That's actually this one, where if I write the terms out using this nth term formula, I won't actually see it like this with the subtraction. To reveal that, I actually would have to do partial fraction decomposition. So just a context clue there, that if you see a rational function as an nth term formula, maybe some partial fraction decomposition would help us determine that that's actually a telescoping sum. Like the geometric series, the telescoping sums, if I notice one, I can not only tell you that it converges, I can find what it converges to. And that's kind of the best thing ever, is when we can actually find the value a series converges to. Next up, we have the nth term test for divergence. It tells me that if the sequence a series is built upon doesn't go to 0, then the series must diverge. So if I look at a series and I look at its nth term formula and say, you know, I don't think when I take the limit as n approaches infinity I get 0, then I'll know right away it diverges. Now, a little bit of warning here, just because this limit is equal to 0 does not mean we have a convergent series. The harmonic series is our counterexample for that. The integral test. I have a series and an nth term formula for its terms that's equal to a continuous function with positive decreasing terms when I plug in the whole numbers. What the integral test tells me is that this improper integral and this series have the same behavior. They either both converge or they both diverge. And the way I always like to think about that is that they have the same behavior. So I have a series. If I have a continuous function with positive decreasing terms, then I can take that improper integral, and if it converges, my series converges. If the improper integral diverges, then my series diverges. When I'm looking at a series, I might apply that if I think I can integrate easily. The drawback here, I'll know whether it converges or diverges. In the cases where it converges, I'll have no idea what the actual sum is equal to. That's where the telescoping and geometric things have an advantage. And then finally, 2 comparison tests. The direct comparison test, which in some books is just called the comparison test, and the limit comparison test. The direct comparison test requires me to have two series whose nth terms obey this inequality. They both have to have positive terms, and there's a big one and a small one. If I happen to know that the series based upon the larger nth term formula converges, then the one built upon the smaller one also has to converge. If, on the other hand, I happen to know that the series based on the smaller nth term formula diverges, then the series based on the larger one also has to diverge. In the direct comparison test, it is up to us to choose a series to compare our series to, which means I have to have some intuition about whether I think my series converges or diverges. Because if I think the series I'm trying to learn about converges, I need to know a series that's larger than it, whose nth term is on top, that I know converges. And vice versa for the divergent ones. If the one I'm trying to learn about, if I think it diverges, I need to figure out a sequence whose nth terms are always smaller than the one I'm trying to learn about that I already know diverges. And of course, the p-series are great examples there. And if not p-series, geometric series make nice things to use in these comparison tests. The limit comparison test has me find a limit. I have to have series based upon sequences with positive terms for some n greater than or equal to n. If the limit as n approaches infinity of the quotient of those two nth terms is a constant, then the series either both converge or both diverge. And there are two more parts to the limit comparison test written down in our textbook, and you can take a look at that whenever you like. But to date, we have 6 different ways of learning about whether a series converges or diverges. And not so coincidentally, I had 6 examples. So what I'd like to do now is to choose to use each one of these ideas one time to solve these 6 problems. And that's how we'll end this video, just by looking at these examples and picking which thought here. There's a geometric series in there. We're going to find it. And then we're going to choose to use a limit comparison test, direct comparison test, integral test, and all of these exactly one time. And so what I would challenge you to do now is to pause the video and think about those 6 different ways we can learn about series convergence and pick which problem you're going to do that way. I promise you there's more than one right answer for each one. We could definitely use the direct comparison test, the limit comparison test on geometric things or telescoping things. I'm just choosing to use all of these things we just talked about exactly once as a challenge for all of us. So there's a geometric series somewhere in here. There's a telescoping sum somewhere in here. There's something I can use the integral test on, at least one thing in there. There's something that I'll use the nth term test for divergence on. And then I have 2 comparison tests, the direct comparison test and the limit comparison test. Pause the video here and see if you can assign each one of these to one of the problems. And again, there's more than one right answer, but I'll go through here in a minute and do it. All right, so I'm not going to go 1, 2, 3, 4, 5, 6, even though I could, because I don't know. I think I could probably do the integral test on many things, and then the 2 comparison tests on many things. So I think I actually want to use this as my organizing thing. I want to find the geometric thing before I move on. If there's only one of these that's geometric, or even if there are 2 that are geometric, I want to go on and get which one I'm going to choose to do the geometric sum thing on right now. All right, so looking through here, I need to think about things that might be geometric, and those are things that grow every single time I plug stuff in. And the one I see here is this one, because I see so many things raised to an n or n minus 1, n minus the first power. 3 to the n, 2 to the n minus 1, 7 to the n minus 1. So what I'm going to do is I'm going to choose to think about this one as a geometric series. So I'm going to rewrite it a little bit, and then I'm just, hopefully, in the next video, going to find its actual sum. Then most of the work for this one will happen in this video. So when I'm looking at this one, what I'm going to choose to do, and I could just write out some terms to notice it's geometric, but I'm going to be a little sneaky here. See, that n minus first is bothering me. So I'm going to divide everything by 2 and rewrite that as a 2 to the n. Right, because 2 to the n minus 1 is the same thing as 2 to the n over 2. Right, and that way everything's being raised to the nth power. And that lets me rewrite this as a 6 to the n over a 7 to the n. So I'm just going to call that a 6/7 to the n power times that 1/2. Right? I guess I have that 2 on the bottom outside. Now this is really looking geometric. If I think about plugging a 1 in, I can definitely find A, and then R is just going to be 6/7. So eventually we'll work that all the way out, but this is the one I'll use the geometric series ideas to find its actual sum. Next up, I'm looking for a telescoping sum. And just kind of looking through all of these, that actually absolutely has to be this one. Because I can factor an n out of the bottom, and now this definitely looks like a rational function I can use partial fraction decomposition to learn about. So number 5 here, this is the one I'll evaluate the sum as a telescoping sum. I'll actually be able to find its value. Okay, so that gets me through these 2 ideas. I have 4 things to go through. And I actually want to think about the nth term test for divergence next, because if I look at the integrands, I can actually figure out if any of them aren't going to 0. And, well, the power of n on the bottom is larger. The sequence here on the inside is going to 0 if n goes to 0. And that's true for all, except for this one. It has to be this one. So not only do I think this is the one I'll use the nth term test for divergence on, I think it diverges. It's a test for divergence after all. All right, that leaves me 3 ideas left to apply to these examples. Just looking at this one, I think it's easy to integrate, so I'm going to use the integral test on that one, getting that out of the way. That lets me use my comparison tests on these 2. And looking at them, I think I want to use the limit comparison test on this one, because I really don't want to have to explore inequalities in any particular order on this one. And looking at the arithmetic here, I think it's going to be easy to figure out an inequality, the nth term formula, to compare that one to. See, when I see an n minus 1 over an n to the 4th plus 2, right away I'm thinking that maybe I want to compare this to the series 1 over n cubed, that convergent p series. And I think I can convince myself that this nth term formula is always smaller than 1 over n cubed pretty easily. Now, there are other options here. I am sure we could probably find another geometric series here. That might be something interesting for y'all to think about. And then swap things around and do many different ways. But this is a way in the next video or videos that I'm going to determine which of these converge and which diverge. Feel free to try other things, try other orders of these ideas written here and see if there's another way through this set of problems. Assuredly there is. But that's it for now.